Okay, so today I'm going to try something new. Again, using this screencast-o-matic to make a video for you. Hopefully the audio will work because I'm using my smartboard at school. These 5 equations are our kinematics equations. We've derived them previously, and remember that kinematics means motion with a constant acceleration. So let's go ahead and just review how we're doing by looking at a sample problem. Let's see. All right. So a ball is tossed up in the air and returns to the person's hand at the same height 2.5 seconds later. How fast was the ball moving when it left the person's hand, and what was the maximum height the ball traveled? Well, my first idea is that we should set up our columns of information like I do every single time I do kinematics. I have the up column and the down column. Even though the only force acting on the object is gravity, I still need to split it into 2 parts because on the way up it's slowing down due to gravity, and on the way back down it is accelerating due to gravity. Now don't be confused here. The acceleration is always pointing down, and it's 9.8 meters per second squared. But the effect of that acceleration depends on whether we're looking at the up or the down. So I like to think of this as a mirror image problem, where the up will look just like the down because the person caught the ball at the same height they released it. So right now I know this information. At the top of its flight, which is the final velocity for the up and the initial velocity for the down, it is momentarily stopped. That's where the 0 comes from. Notice the signs on the accelerations. For the time, I simply take the 2.5 seconds and cut it in half. That only happens because this is a symmetric problem. If the person tossed the ball in the air and then for whatever reason did not catch it at the same height, the times would not be the same. So the first question says, how fast was the ball moving when it left the person's hand? I have 3 numbers, so I can choose one of my equations. I'm looking for V initial. I don't know anything about D, and I'm not asking to solve for it. Therefore, I'm going to choose the equation without D in it. Once I've chosen my equation, I substitute in my numbers. So the ball is tossed at 12.25 meters per second, and when it returns to the person's hand, it will hit their hand at 12.25 meters per second. To find the displacement or the height the ball reaches, now I can use any of the equations that has D in it. And really, you should be able to check your work by using more than one equation, and they should all yield the same results. I'm going to choose you can call me lazy, but the reason I chose this equation is because V final is 0, which makes this term go away. Because 0 times t is 0. Therefore, I get and this simply becomes becomes a calculator problem to get the answer. So the ball will rise 7.66 meters. Okay, I wanted to start with this problem as review because now we're going to look at two-dimensional kinematics. So two-dimensional kinematics has motion in both the x and the y directions, or the horizontal and the vertical directions. In this particular problem, we have a soda that is slid off a counter, the person's distracted, and so it goes flying. So here's our picture. The important part of this problem is that when it leaves the countertop for that moment, it only has velocity in the x direction. Now we're going to make an important assumption here that most of the physics community would make with us, which is we're going to ignore air resistance, meaning the only force acting on this mug as it's falling to the ground is gravity. Since there's nothing acting in the x direction, the mug cannot speed up or slow down in the x direction. Therefore, the velocity in the x direction is constant. So for our x direction, I only have three variables. The velocity in the x direction, which will remain unchanged, x displacement, measured in meters, and the time, t, in seconds. Now in the y direction, it's a kinematics problem because gravity is accelerating the mug downwards. So we'll have all five variables. There's some great ways to show you that x and y are independent of each other, but for right now, I'm just going to tell you they're independent of each other, and we'll have to do some looking into this later. Alright, so as the mug is traveling through this parabolic path, Vx remains the same, and Vy is increasing at 9.8 meters per second every second. In fact, right before it hits the ground, it will have both x and y velocities, which means we're going to have to add the vectors to figure out the velocity right before it hits the ground. So in that blue triangle I just drew, we have Vx, Vy, and then the hypotenuse I would call V total. Okay, so what do we know from reading the problem? It strikes the floor 1.4 meters from the base of the counter. I also know that in the beginning, it leaves the counter with a V initial of y of 0, and the counter is 0.86 meters high. So it looks like I have more information in the y direction than the x direction, which is true. The other thing I'd like to point out is however long the mug has to fall down is the amount of time it has to fall over. So the times in this case are the same. All right, so let's see. It says, what is the mug's initial velocity? Well, to find Vx, which is the initial velocity, we need to know the time it falls. So let's go to the y side and find the time. Choose the equation without V final. Sorry, wrong equation. Without V final. D equals V naught t plus 1/2 at squared. Substitute in. Depending on your algebra skills, you might want to take some time and look at this. But basically, you're going to take 0.86 and divide by 4.9, which happens to be half times 9.8. And then you're going to take the square root of that answer to get 0.42 seconds. So the mug's flying through the air for 0.42 seconds. Now I can actually figure out how fast it was going when it slid off the countertop. When you have an object going at a constant velocity, you do not need to do kinematics. You can just use v equals d over t. Or in this case, vx equals x over t. So I take the horizontal distance and I divide by the time. And I get an initial velocity of 3.33 meters per second, which is the x velocity for the entire path. I'm actually going to redraw this parabola here and show that this is 3.33 meters per second. Now I want to find this velocity vector. Now, depending on your comfort level with vectors, we might have to have a conversation about whether this final velocity is in the third or the fourth or the first or the second quadrant. It looks like the fourth quadrant because we have a positive x and a negative y. Really, in physics, you get to say what's positive and what's negative. So I'm going to go ahead and call down, in this case, the positive direction. So I need to find that leg in the y. So I go back up. I choose v equals v naught plus at, and I get v equals 0 plus 9.8 times 0.42. Use my calculator, and I get 4.12. Okay, to finish up this problem, we need to do Pythagorean theorem to find the actual magnitude of the total final velocity. So 3.33 squared plus 4.12 squared, the square root of that answer gives me 5.30 meters per second at theta equals, I'm going to go ahead and show a negative to show that I'm going to go around this clockwise as opposed to counterclockwise the way we normally do. And to find the angle, I always use tan inverse of the y leg divided by the x leg. I get negative 51 degrees. Remember, theta equals tan inverse of 4.12. So that's a half parabola problem. This is our introduction to two-dimensional motion. We keep the x and the y separate. The x direction has no forces acting upon it, so there is no acceleration, which means velocity is constant, and we can use v equals d over t. And in the y direction, there is gravity, which is causing acceleration, so we actually do all 5 variables and do kinematics. All right, in the next video, I'll show you a full parabola and an uneven parabola, looking more at two-dimensional kinematics. Thanks.